Thank you for participating in this webinar replay. My name is Jean-Rémy. I am the representative director of DPS Kabushiki Gaisha. I'm going to present you with a study that we carried out in partnership with the Renault Group, and this study concerns shape optimization. It focuses on the water jacket of the cylinder head of a combustion engine. It deals with durability and fatigue life improvement using Tosca structure in combination with Abacus and EFISAFE. After an introduction, I will talk about the preliminary works of the study, and I will devote part of my presentation to the concern of the approximation model. We will then discuss the definition of the optimization process, and I will show you some of the results we have obtained. And I will finish with a conclusion and will open the discussion to your question. I will be brief. DPS is a French company. It was created in 1997. Its subsidiary, DPS Kabushiki Gaisha, is much younger, established in 2017. We have offices in France, in Paris, and Toulouse, in the USA, and in Japan. DPS is about 100 engineers. We are technical specialists with expertise in what we call CAD and CA integration. DPS works with most major industrial groups from several industries: automotive, aerospace, defense, and energy. By providing services and software to our customers, we help them integrate the simulation of their complex product earlier in the design process. We have a triple expertise in CAD, simulation, and programming. We are in Japan since 2012 with Honda, the major customer of DPS KK, and with Toyota more recently. Okay, let's move on to more technical considerations. Well, when it comes to increasing the durability of mechanical components, such as engine, the conventional and fairly simple approach is to reduce strain and stress concentrations on parts. Unfortunately, in complex cases, because of the cyclic nature of the loads, the location of stress peaks is often different from the area of maximum fatigue damage. The combination of structural analysis and fatigue software is a first step towards improving the durability of a system. And at this point, we can also consider adding shape optimization tasks to the process to identify the minor changes in geometry that will have the greatest impact on the lifetime of the system. That is what we did. And we have defined for the group Renault an innovative methodology based on the SIMULIA portfolio, Abacus, EFISAFE, and Tosca structure. Tosca structure is a non-parametric structural optimization software. It provides four main optimization models. The idea of the topology optimization model is to change the general layout of the component. We define a specific objective for the maximum stiffness structure or to minimize the weight, etc. The solver will remove material until the objectives that have been defined are reached. With shape optimization, we modify the surface of the component. This is the technique we use for this study. Sizing and bead optimization apply to shell and beam structures. With sizing optimization, Tosca looks for the best arrangement in terms of element thickness or beam property with regard to static or dynamic behavioral objectives. The bead optimization model suggests the creation of optimized bead patterns. This will increase the bending stiffness of the part and, in some cases, the eigenfrequencies of the sheet metal structure. If it is no longer possible to make large changes to the geometry, you will probably want to perform shape optimization. The typical reason is to homogenize the level of stress and eliminate the local hotspots. The parametric and morphing approaches are very similar. Depending on the number of parameters involved, you can implement a design exploration method to find the best configuration for these parameters. This can be done with eyesight or 3D Experience Process Composer. But the most generic approach, one that offers the best benefit potential, is definitely a non-parametric approach. you do not need any parametric model. The setup is very simple. It considers the nodes of the surface and adjusts their positions as a freeform. We use this method with Tosca structure in our study with Group Renault to determine the optimal surface contour of the water jacket. I will not go into the details of this slide. Our CAE model is an assembly of several parts. This represents about 1.4 million of elements, 2.2 million nodes. The cylinder head parts has a finer mesh. It alone accounts for 80% of the number of nodes and elements. Inside the cylinder head, the water jacket surface of rather complex shape presents the finest mesh. The Abaqus simulation that we have set up is very common for this type of problems. 8 steps have been defined. Initialization steps, steps of heat transfer and combustion, with thermal loads and combustion resulting from 3D CFD simulations. In this study, 2 thermal cycles are applied. Each thermal cycle comprises 2 steps. Between them, the cylinder head is cooled to the minimum operating temperature. Thus, the nodal temperatures of the last 2 steps representing a thermal cycle are assumed to be a steady-state solution. Of course, because of the definition of contact and the material, the problem is nonlinear. For this study, the prediction of fatigue life is calculated by FE-safe using the Abaqus stress field and resulting from the thermal cycle. Regarding fatigue, the Dangban criterion is a very common standard. Only a few physical tests are necessary to determine, for material, the characteristics of the Dangban domain. Hydrostatic pressure and the level of shear stress during a cycle are major factors in the fatigue strength of a part. If we trace the load path followed by an individual grain of material during the cycle, we can determine a fatigue safety factor, defined by the ratio between OA to OP. If FSF is greater than 1, the criterion predicts that no cracks will be initiated near this grain. On the contrary, if the criterion is lower, a crack will occur, causing the area to fail. The practice at Group Renault is to add a safety margin when using the Dangban criterion. With this modified criterion, the fatigue safety factor was evaluated over the entire surface of the water jacket. In doing so, 3 critical areas have been identified. Well, given the size of the model, the type of computation, since the shape optimization consists of 15 to 40 iterations, it is clear that the computing time could be very long. As such, for industrial applications, the duration is not acceptable. So what to do? Well, we need to reduce the Abaqus computation time and the number of iterations of Tosca. In order to reduce the Abaqus computation time, several possibilities have been imagined and tested. Increase of the mesh size, change the contact pair by specifying tight conditions, etc. You can see a comparison between the reference case and some approximations in terms of computation time and accuracy. The best compromise is the linearization of the CAE model, which consists in changing the quadratic element into linear elements. In this way, the computation time becomes acceptable, 1 hour and a half. It was about 50 hours with the reference case, while the fatigue safety factor deviation is only 17%. I will discuss later how we took this deviation into account. So we implemented an optimization process with Abaqus and FE-safe, controlled by Tosca structure. Thermal and structural simulations are performed by Abaqus, who transfers the result of the stress field to FE-safe. Then, FE-safe calculates all variables related to fatigue life prediction, such as the local values of the fatigue safety factor. The shape optimization is entrusted to Tosca structure. Tosca offers several algorithms to drive optimization. The best choice in our case is the algorithm called controller-based algorithm. One of its advantages lies in its very fast convergent capability. Using this algorithm, a maximum of 15 to 20 iterations only are needed to obtain the optimal solution. It is very interesting in our case. This will help us limit the computation time. Regarding the setup of the shape optimization case, two main things must be defined. The first is what we call the design space. This is the region where optimization is free to modify the shape of the component. We have defined a very local area. It is composed of nodes for which the fatigue safety factor is less than 1 plus x. The second point is the definition of the objective function. In our case, we define a maximization function. We want the process to maximize the fatigue safety factor. We especially want to increase the minimum value of this factor. Our approximation model returns an overestimate of the fatigue safety factor. This is shown on these two images. For this reason, we increase the objective value by 17%. We also define a non-design space, meaning the precise regions where the modification of the shape of the component is strictly forbidden. This corresponds to holes, machine valve seats, etc. We have also defined the constraints of the shape optimization. These constraints are mainly limitations for maximum and minimum displacements. They come from the analysis of the preliminary Abacus results and the Group Renault's business expertise. If we allow some nodes to move, we need in some cases to generate a smooth surface. Mesh smoothing is performed internally by Tosca structure during the shape optimization. It is done not only on the elements belonging to the surface, but also on the element located inside the part. Because it avoids the distortion of the mesh and controls the aspect ratio of the elements, the smoothing preserves a high mesh quality at each iteration of the process. This ensures that the finite element analysis quality will not be affected by the stretching or contraction of the elements in the optimized areas. After defining a design space, constraints, and optimization objectives, we can start the optimization process. Here is the evolution of the fatigue safety factors of the three areas. It shows you the improvement we can achieve after a loop of 20 iterations. But speaking of optimization strategy, we have also implemented a technique to reduce the number of iterations. It is based on splitting the optimization into three distinct tasks, one task for each area, and the definition of local stops criterion. Here is the result. First, the total number of iterations have been reduced from 20 to 16. But more than that, when a stop is triggered, which means that the local objective is reached, the rest of the computation progresses faster because the process focuses only on the remaining areas. Let's talk about the results we got. First, in terms of geometry change. Here, for the three areas, you have an enlarged view of the shape obtained at the end of the optimization process. The precise figures are confidential, but I can say that the maximum value of the displacements is less than 3 mm. Looking at this map of nodal displacements and referring to the previous slide, which shows through optimization a significant improvement in the fatigue safety factor, you need to be sure that small changes in geometry can have a significant impact on the reduction of peak stress and fatigue lifetime of components. After this, we performed a validation run. For this, we switched back the Abacus model to quadratic elements. We got this final result for area 3, which was the least critical area. For this area, the initial fatigue safety factor was very close to the objective. Durability has been improved very quickly. One remark: for some spots, the FSF calculated with quadratic elements is slightly less than 1 plus x. Two explanations. First, the smoothing in this area is maybe not perfect, and second, in areas where the FSF value is already high, the deviation from the approximation model is certainly greater than 17%. This means that we should have set area 3 a higher objective. Area 2 was a little more critical. The initial value of the FSF in this area was close to 1. The optimization process increased the safety margin, and almost every element of this area have reached our objectives. For area 1, the improvement is very impressive. It was the most critical area, and the minimum value of the FSF was less than 1, expressing a real risk of failure. After the optimization process, the durability is really improved. All elements of area 1 now have an FSF greater than 1 plus x. This is clearly the most important result of this study, and this represents for us and Group Renault a great success. Well, the time has come to wrap up. DPS has successfully developed for the Group Renault what I believe to be an innovative process, not only in terms of shape optimization, but more generally with regard to improving durability of components. The use case presented today is a real industrial case. DPS has implemented this methodology by leveraging the SIMULIA portfolio, which offers a complete solution for realistic simulations. This is very positive for our customers. This helps them reduce the risk of fatigue failure of their cylinder head. This methodology shows an impressive improvement in fatigue safety factors in areas where risk existed prior to optimization, while the computation time has become totally acceptable. With regard to the perspective we are working on, the first, we would like to improve the definition of mesh smoothing. We believe that a better mesh smoothing can improve result and reduce the time needed to redefine the shape locally. The second, we would like to further reduce the computation time, and for that we are currently studying the possibility of using submodeling techniques. And last, we are thinking of other components that can benefit from this technique. Thank you for your attention. Give me a thumb up if you think this content is of interest to you. Put a comment below to start a conversation. And do not hesitate to contact us for clarifications.